Hi, my name is Dr. Harvey Miller, and welcome to the second part of our inventory management lecture, which focuses on the reorder point model, but also the production order quantity model, and some, level of uncertainty in terms of reorder points and how we treat that. Also, too, we will talk briefly about what we call the periodic order or periodic review inventory system, in contrast to the continuous review inventory system. All right. So this course is part of our course on operations management as part of the business program in the Sobey School of Business at St. Mary's University. So what we want to talk about is the idea of reorder points, safety stock, as we said, single period model, and fixed period systems. In the first part of the inventory management chapter, we focus on the question of how much to order. We say that there are two key questions we want to answer. One is how much you order. The second question is when to place the order. So if you have a small business and you're managing your inventory, your stock levels, when you place an order, should it be for 1,000? Should it be for 500? Should it be for 300? And then do you place your order weekly, or do you wait till inventory gets to a certain level before you actually place the order? All right. If the inventory gets to a particular level before you place the order, that's a reorder point. And so your level is fixed, but the time it takes to get to that point might vary depending on if there's variability in the demand. And then we simply place the order and we get a fixed quantity. But if we're talking about a periodic review system, we look at the inventory level on a regular basis, say for example weekly or monthly, and then based on the inventory level that's there, then we place an order. And the amount that we order can vary depending on how much inventory we actually have in stock. It's kind of like if you normally buy, say for example, um, 2 cartons of milk, all right? And but you're checking weekly. You're looking at your refrigerator. You say, "Oh, do I need some milk?" So if you're down to like half of, say, the second carton, then you might decide, okay, when I go to the grocery store, I will buy 2. But if when you checked, one is unopened, you're not going to buy 2 because when you can return, you will now have 3 of them in stock. You will now just buy 1. So the amount you ordered changed because of the current inventory level. You already had one unopened one and one that's almost finished, so you just basically bought 1. But if you had 1 3/4 completed and finished, then you would actually buy 2. So in that periodic review system, the amount you order will vary based on what you have in stock. Whereas in the continuous review system, when your inventory gets to a particular point, because you're monitoring it continually, then you place a fixed order to arrive at a certain time. Okay. So as we say, the reorder point (ROP) tells us when to place the order, and so I need to just change. Let's see here, one of those. We have to change that to black because I cannot write. Here we go. All right, here we go. Oh, I just realized I'm talking, but I have not changed my I have not changed my iPad yet. But here we are. Okay, so we're talking about reorder points, and I just sort of explained to you what that meant. So in computing the reorder point, we often need to know what the lead time is, and we need to know the demand during the lead time. And so there's a very simple formula which basically says your reorder point is the demand during the lead time multiplied by the lead time. So if while we're waiting for the items, the average demand is 20 per day, and if the lead time is 5 days, then you will wait till you have 100 units left and then place the order. It's fairly straightforward. Now, this is a case where there's absolutely no uncertainty. The lead time is predictable and the demand is predictable. But what if they were not predictable? What if demand could vary? What if lead time could vary? We now have to add something that we call safety stock. So safety stock allows us to hedge against that uncertainty in the demand or the lead time. All right? And so we'll talk a bit about that a little bit later. This diagram just shows you what we're talking about in terms of reorder points. So we have our inventory being used up at a constant rate. The slope is D. All right, that's the D units per day. And then knowing what the lead time is, we want the inventory to arrive at this point. So if our lead time is L, we sort of work backwards L units, so which brings us to here. And then if we simply were to come up, butt up against this graph, that tells us what our reorder point should be. So when the inventory is going down and it gets to ROP, our reorder point, then we're going to place the order at this point in time, right? So that reorder point corresponds to this point in time over here. And remember, it is going to take L units in terms of days or weeks or whatever it is that we're measuring time in. For the order to arrive, it will arrive at this point exactly because it is what we call deterministic. There's no uncertainty, and the cycle repeats itself. So we get instantaneous replenishment. That's like basically your package is just arriving, and then just you put it into stock. And then the cycle repeats itself. I have to make this slope the same, draw this parallel, right? And so the same idea, if I work backwards to L, if I drew this properly, it should be approximately the same. There you go. All right? So that's L, and then the next order will arrive here as well. So that is the case where we have determined our reorder point. There's no variation in the demand during the lead time. There's no variation in the lead time. So ROP is just the amount of inventory you have on hand to cover your demand during the lead time. So if my daily demand is D and my lead time is LT in days, then it's just D multiplied by LT. So if I had 50 units per day multiplied by 3 days for my lead time, then my reorder point is 150 units, ROP. That's as simple as it is, all right? So I think we have an example right here. 8,000 iPhones per year is the demand. I'm pretty sure it's more than that globally. But then maybe this is a particular store or group of stores. 250 working days per year, and the lead time for orders is 3 days. It may take 4. So let's look at our daily demand. It would just be our annual demand, right? Divided by the number of working days per year. So it would just be 8,000 divided by 250, which we see is 32 units per day. All right. And then our reorder point would be the 32 units per day multiplied by the 3 days for 96 units, or 32 units per day by 4 for 128 units. So it could either be 96 or 128. In this case, we would have to really collect some data to firm up exactly what their lead time is, and then use that, because you can't be using two quantities for your lead time. Okay, we want to now introduce you to a slightly different model called a production order quantity model. This is a variation on the economic order quantity model where you have what we call simultaneous production and usage. The kind of silly example I could give you of that is if I'm making cookies or loaves of bread, and say I'm making 100 loaves per hour, but I'm consuming 10 to make sandwiches per hour, then at the end of the hour, I only have 90 loaves. I don't have 100. So even though my production rate is 100 and the time frame T that I'm looking at is 1 hour, I should have 100 loaves in 1 hour. But then I'm consuming, so this is my production rate, right? The 100. But if I'm consuming, my demand is 10 per hour. Then my accumulation rate will be P minus D, which would be 100 minus 10. So I'm now accumulating at 90 per hour. So depending on how long I produce for, that will determine what my maximum inventory level is. Okay? So let's assume that I'm going to produce here, let's look at this. I'm going to change one of these colors. I'm going to change it to white here. So let's assume I want to produce Q units. Well, how long is it going to take me to produce Q units if my production rate is P? So this is the order quantity. P is my production rate. So the time it's going to take me, T, is going to be Q over P. There you go. All right. So it means that let's say I'm going to now produce for T units of time. My maximum inventory that I will accumulate, Imax, will be P minus D times T. But remember, T is the total time it takes to produce the Q units. So therefore, my maximum inventory, I could rewrite it as P minus D times Q over P. Make sense? If I bring the P underneath the P minus D, I could rewrite this as Q times P minus D over P, which is the same as 1 minus D over P. So that would be my maximum inventory. Now notice that this will be less than Q. It makes sense because, like I said to you, if I'm making 100 loaves per hour and I'm consuming 10 of them to make sandwiches at the same time, and some will be sold as bread, by itself, not as sandwiches, but bread. Then the amount that I will actually have accumulated will be for sale in terms of as loaves will be 100 minus 10, which is 90 units per hour. So depending on how long it's, based on the quantity that I want to produce and how long I want to, so it will tell me how long it's going to take me to produce Q, then I will know what the maximum inventory level is, which is Q times 1 minus D over P. All right? And then I could now use that IMAX to calculate the inventory cost. Now remember, when we cut in an inventory management model, when we calculate an inventory cost, it is the cost on the average inventory. In the EOQ model, where we did not have simultaneous production and usage, our inventory cost was the average inventory Q over 2, right, times the holding costs. And that's because Q was the maximum amount of inventory. Well, in this model, what is the maximum amount of inventory? It is Imax. So it will be Imax over 2 times H, the holding costs, which we could actually put now Imax over 2. Remember, this is Imax right here. So if we're going to divide it by 2 multiplied by H, we could put it as Q over 2. I'm dividing the Q by 2 times the 1 minus D over P times H. So that would be the holding cost now for the production or the quantity model. All right. So it is modified. Why? Because the inventory level that we're going to have is going to actually be less than Q itself. And that's what this portion is really telling us right here. That's our Imax. It's going to be less than the original Q. If there's no simultaneous production and usage, then what would happen is that D, right, and over P, this part will be 0. There'll be, we're basically just getting all our production, right? There's no demand. So D, no usage at the same time. So the D would then be down to 0. and then and in which case our inventory level will go to a maximum quantity of Q. All right. So all I've explained a while ago is actually what is being written right here. So Q, the number of units we're going to produce. H is the holding cost. T is the length of production in days. The daily demand rate or daily usage rate is D, and then P is the daily production rate. And so annual holding costs is basically the average inventory times this, but the annual is the maximum inventory divided by 2, which is Imax over 2, and I showed you how we calculate that. The maximum inventory level would be the total amount that you produce minus the total amount that you use, which what we said was P minus D times T. All right, but we know T, our production run, is Q over P, which I showed you earlier, and we use that. So here it is, our production run is Q over P, and then doing all of the substitutions. This looks a little complicated, but I showed you. All they're doing is substituting for T in that formula over here, Q over P, Q over P, and then we sum it up to this right here. Q1, now this is an error. This should actually be D. I made a mistake here. So it should be Q times 1 minus D over P. And then, of course, if we multiply it by H, then we get the formula that we are interested in. Now, again, they're making mistakes in these diagrams. That H should be on the outside. H should be here. It should not be on the inside. All right? And I showed you that before. This Q over 2 times 1 minus D over P times H. All right, so having done all of that, great stuff. If we go through the process of finding the economic order quantity like we did in part 1, without running you through all the calculus and everything, you will end up with the following formula. All right, the formula would be the optimum order quantity Q is equal to, notice it looks like the EOQ model, 2 times D times S, which is 2 times the annual demand times the setup costs, over H. Now that would have been the EOQ model, except that now we have to adjust because we are holding slightly less inventory. We are holding less inventory, so we're adjusting by this factor D over P. So what does that do? What it does, it reduces the effect of in terms of our holding costs, right? Because not all of the units that we produce are going to be held. Only a portion of it is going to be held. What's that portion? That portion is 1 minus D over P. All right? That's a portion that's been. So essentially, we have to kind of adjust our holding costs by that factor. What is the impact of that? It reduces the denominator in this function, and as a result, it will make Q higher. So when you compare the same basic data to an EOQ model, because we are going to end up holding less inventory, it means that we could actually produce more. So the Q star for the POQ model, or we actually sometimes refer to it as POQ, the POQ, the production order quantity, that will tend to be higher than EOQ because of the fact that we will be holding on average less inventory as a result, so we can produce a bit more. Okay? All right, and then I believe we have an example where our annual demand is 1,000 units. Our production rate is 8 per day. Our demand is 4 units per day. So we'll be accumulating at 8 minus 4, right? Which is basically P minus D, which is 4 units per day. That's what the way in which we're going to be accumulating. So what will our maximum inventory be? If we are producing 8 units per day, and depending on what our order quantity is, we could determine that quantity divided by 8 will give us the number of the time that we are spending producing, and when we determine that time t, which we know is Q over P, but we don't know exactly what it should be yet. I'm just saying if we knew what it was, we would calculate T, and then if we multiply the rate at which we're accumulating inventory by T, the production period, we would know what our maximum inventory level is. We've already gone through that. Just sort of putting it in the context of these numbers that we have here. Anyway, the first thing we got to do is to compute our optimum order quantity from this problem. Given all the data that we have, this is the formula, as you know. So 2 times our demand, which is 1,000, S, which is our order cost, which is 10, and then our holding cost per unit per year is 50 cents, and then we multiply by the factor, which adjusts it for the fact that we have simultaneous production and usage. So we get a total of 283 hubcaps is what we would produce. So if you think about this and you say, well, how many production days does that represent? Well, we would have to divide it by 8 to find out how many production days that is. All right, 8 into 28, 3 8s are 24, and 43. 43, so 5 8s are 40. We have 3 left. So our total production time is 35 and 3/8 days, right? For approximately 36 days is what we're looking at. And then if we want to know what our maximum inventory level is, we would have to multiply this amount by 4, because that's our total number of production days. And remember, we said we will be accumulating at a rate of 4 per day. So we could compute what our maximum inventory level would be. And let me see if it's on the next page. It's not actually shown, but it would have been essentially 35.38 days multiplied by 4 per day. Right? Multiplied by 4 per day. Now, I believe this was actually 283 over 8 multiplied by 4. That would go into 2. So if we divide this by 2, will give us 1, 28 is 4, 141. We have remainder 1.5 units, hubcaps. So that's our IMAX. All right? Remember, what is IMAX? IMAX is your number of days you're producing. That's our T times P minus D. That's IMAX. And here we go. That will give us 141.5 hubcaps would be our maximum inventory that we would incur. Excellent. All right. So that's the production order quantity model. And like I said, it's used a lot in environments where you have simultaneous production and usage. So in assembly line systems where you're producing a component and that component is now some of it is being used at the same time as part of an assembly. Okay, if you are in a bakery and then you are producing while selling at the same time, you might be very well producing, you need to be producing faster than what you're selling, otherwise you'll run out of stock. So if you're making croissants, you might be making 50 croissants an hour, but selling 10 an hour, right? In which case, then your accumulation rate is 50 minus 10, which is 40 croissants per hour. Excellent. Okay. That is the production order quantity model. Let's talk a little bit about this idea of quantity discounts as another inventory model. So some manufacturers or some retailers might offer you a discount for purchasing larger quantities. The idea is to encourage you to order larger quantities. So the decision that has to be made is the trade-off between, am I saving enough on the purchase cost of the item compared to the increased price of the carrying cost? Because if I normally order, say, 500 units, but the retailer is saying to me, hey, or the wholesaler, buy 2,000 units and I'll give you a 20% discount. You have to say, is that 20% discount worth it? And it would be worth it if the total value of that discount is more than the cost of carrying extra inventory, because your order quantity was 500. Now your average inventory is going to be, instead of 500 over 2, which is 250, it's now going to be 2,000 over 2, which is 1,000. So is the increased cost, annual cost, worth it? So you see, what will happen is that these wholesalers will offer you ranges and say, if the initial price, if you buy under 120 units, will be $100 per unit. So this is an example. But if you buy between 120 and 1,500, that's a big range. Well, we give you $2 off. And if you buy more than 1,500 units, we will give you $4 off. Is it worth it? So in this case, we have to consider not only the cost of carrying inventory, ordering costs, and holding costs. We have to also consider the purchase cost, because remember, the price changes depending on the amount of that you order. In other words, price is a function of the quantity, right? The price of the item. So here is what we're looking at: our order quantity, our annual demand, our holding costs per unit, and S is the ordering cost. I don't know why they didn't just change it to H. Why they use I, but it very well could be H as well. So don't be confused by that. Okay, and so expressed as a percentage I. Okay, so I is a percentage of the price. That's why. Normally I use small I, like interest. So holding cost per year expressed as a percentage of the price. That's why we're using I and not H. So H actually is I times P, purchase price. Okay. So the way in which you approach this is better to show you as a diagram, but then let me just show you the steps. So starting with the lowest possible purchase price. So of course you go for the best price. Let me see. If I go for the lowest possible price, can I get an economic order quantity that's feasible? And if the answer is yes, great, then you don't need to do anything else. Take it. But if it turns out that it is not a feasible economic order quantity, in other words, the economic order quantity for that price, let's say we said the very lowest one was if $96 for 1,500 or more. What if that EOQ, based on that price, was actually 1,200? Well, you cannot order 1,200 and get that discount. So you have to now say, okay, let me just order the minimum to get me the discount. And that minimum is 1,500. So I'll order 1,500. Okay? So, and then now you now compare it to, you actually continue until you find the EOQ, the economic order quantity, that is feasible. So maybe if I try between the 120 and the 14.99, I'll get a feasible EOQ based on that price. If that's the case, now you say, well, okay, that's the best order quantity for that range. You compare the total price of that order quantity to the price of getting into the lowest cost, which was the 1,500. So now you have to compare them, okay, to see which one is better. So what we do in this case is we look at all the cost curves. So you can see the very first one that's under 120 is this guy right here. Then between 120 and 1,500, that's a pretty big range, as I mentioned to you here. And then the third one, which is more than 1,500, right? So these three curves represent your different pricing. So what happened is that if we actually try to get an EOQ for the lowest cost curve, it turns out to be here. Well, it's between 120 and 1,500, so it's not feasible. So what you would do with this, in terms of your costs, sorry, not your cost, finding your EOQ, you would simply go EOQ is 2 times D times S over I times P, right? Where in this case you would use the price for the lowest cost because that would have been the $96. Well, that EOQ is not feasible because it's somewhere in this range. So to get that price, you would have to order a minimum of 1,500 units. So you say, well, let me find the cost of 1,500 units. But we don't have the answer yet. We now must go with the next cost curve, which is this one, and see what is the EOQ for that one. Is it feasible? It turns out the EOQ is in the range. So why don't we calculate the cost of that EOQ? So the second one, total costs based on the EOQ. We will compute that. We don't need to go with this one right here because we know it's the highest cost curve, so it doesn't make any sense going there. So now you're going to compare the cost of the EOQ to the total cost of 1,500, acquiring 1,500. You're going to compare those, all right? And that's what we will do. So this is just showing us our steps where the first time based on the $96, we got 278 drones to order for this problem. So this is a problem about ordering drones and it is infeasible. So we would have to now go with the 1,500 to get the $96. I don't know a $96 drone. It must be a toy. Then we go for the 98 and then we have 275 drones, which is our economic order quantity, which is feasible. So we're now going to compare those two costs. So the 275 is our unit price, is our annual ordering costs, because we know the total number we're trying to order, multiplied by the quantity. Sorry, no, multiplied by the ordering cost divided by the quantity will give us this value. And then we can compute the holding costs and then your product or purchase costs. Add it all up together, 517,155. 517,155. If we now say, let's see what it would cost us to get the $96 price, where we have to order 1,500. This is the unit price. This is what your ordering cost will be. And so your ordering cost is significantly reduced. All right. But look at that. Our holding cost is significantly increased. So the trade-off, and then of course our purchase cost is reduced as well. But the trade-off is not enough. We still have to pay $520,053, which happens to be more than the 517,155. So it makes sense to stick with the 275 units each time we place an order. So that is the production, not production, sorry, the quantity discount model. All right. There are other ways in which you could vary that, where sometimes you get, you get a discount on all the units. That's one approach. But there's incremental discounts. We say, well, if we'll give you a discount on the first 500, then we give you we give you the first 500 you pay at the original price, and then on the next 500 to 1,000 we will give you a discount one, and then beyond there are numbers beyond 1,000, we'll give you another discount. So that's kind of incremental discounts. That's a possibility. All right. So something to just note is that fixed fees might have a tendency to incur larger orders. What it means is that you're trying to reduce your fee per unit, and so you do that. Or aggregation over time over items. Sometimes you spread a discount over multiple items that are not necessarily the same, but what you do is you just aggregate your discount across a group of items, right? Or maybe over time, you might say, if you're ordering between January and March, then we'll give you a certain discount. Okay. And then you have things like buy one, get one free. These are forms of discounts as well. Okay. So that brings us to the end of the quantity discount model. Now we want to talk a bit about probabilistic models and safety stock. What is it? So we already talked about the idea that a reorder point is the demand during the lead time, right? that you're trying to cover. So if we know the number of units per day, for example, and the number of days, that's the lead time. If there's no uncertainty, it's relatively simple to do. So in a case like that, we would simply just multiply the demand by the lead time and get the answer. But when there's uncertainty in either the demand or the lead time or both, we need a slightly different formula because we now have to incorporate what we call safety stock. And the safety stock that we will incorporate will depend on our service level, our desired service level. And what do I mean by your desired service level? It means that we have to determine what percentage of the demand during the lead time that we want to cover. If we're willing to cover 80% of the demand during the lead time, then our service level during the lead time is 80%, and that will tell us how much that we need to keep in stock. Okay, and that's a very important decision that has to be made because the higher your service level, the more safety stock, the more holding costs. So so the idea is if there's uncertainty in terms of the demand during the lead time, so this is to help you guys remember a little bit of the normal distribution which you did before. So that would be the demand during the lead time. I'm going to put it as DLT by Y because it's an average. And then there's sigma DLT, which is the standard deviation of demand during the lead time. All right? Standard deviation of demand during the lead time. So if we said that there was no variability, we just needed to keep this much. That would be our reorder point right here. But because there's variability, we need safety stock. So we have to add an amount, SS, all right? Safety stock. So if we go there, so what if that took us to this point right here? So what that means is that this would be our probability of meeting the demand during the lead time. This would be our probability of not meeting the demand during the lead time. So this piece right here is our service level. So if we say that's 0.9, for example, our service level is 90% of chance of satisfying the demand during the lead time. Then 1 minus the service level, which is 10%, will be the risk of a stockout. Okay, so you're trying to balance what's the risk of a stockout with the risk or the cost of carrying excess inventory. So your safety stock is this piece right here. Whoops. That's your safety stock. Okay. And so any demand beyond that now is going to be a stock out. So your average demand during the lead time plus your safety stock, and so it means at that point here is our reorder point. Okay, so you need a little refresher, of course, in terms of your normal distribution and all that stuff. So if you may recall, for normal distribution, and why am I using normal distribution? That's because we assume that the demand during the lead time is normal with a mean DLT bar and a standard deviation sigma DLT. Notice I didn't say D, I didn't say just LT, I said DLT, demand during the lead time. So you may recall that Z is equal to, well, let me just kind of take you back a little bit. We used to have the formula look something like this. X minus mu over sigma. Well, in this case, our X is our reorder point. Our mu is our demand during the lead time. And then here's our standard deviation. So that would be your reorder point minus the mean, which is DLT bar, over sigma DLT. And that would be our Z value. So if we had a if we had, and that Z is based on your service level. And so if we look at this formula, essentially it looks like this. Our reorder point, if we arrange everything, reorder point, if we arrange everything, and I should say rearrange everything, would be our demand during the lead time plus our safety stock, right? Which is Z service level sigma DLT. So that piece right here is our safety stock. If there's no variation in the demand during the lead time, then the safety stock is zero. If there's variation, then it's not zero. All right. Now, there are a couple of variations of, I'm going to do this ahead of showing you the PowerPoint slides because then it's faster. There are a couple of variations. So let's say lead time and demand. And then we want to look at the standard deviation. Okay, or I should say, yeah, the standard deviation. So the reorder point and the standard, first of all, let's get the standard deviation. So if this is constant, I'm going to put for constant and constant, then the reorder point is just D times LT. All right. If the demand is variable, and this is a constant, okay, the demand is variable, the lead time is constant, we now have some variability we have to worry about, so we need some safety stock. So this will be, your reorder point will now be D bar times LT plus Z for, remember the Z is based on our service level, ZSL, and the standard deviation for this problem is the square root of the lead time times the standard deviation of the demand. Notice I didn't say standard deviation of the demand during the lead time. The standard deviation of the demand during the lead time happens to be all of this. Now, I'm not going to try to prove that to you. I just need you to just accept that that's what it is because it requires a little bit of mathematics to show you that. So when the demand is variable and the lead time is constant, then the standard deviation of the demand during the lead time is the square root of LT times the standard deviation of the demand. When the demand is constant and the lead time is variable, then it is D, notice the demand is constant, times LT bar plus ZSL, depending on our service level. And in this case, it turns out to be LT times, no, sorry, not LT, it just turns out to be D times sigma LT. Notice that will be the standard deviation of the lead time. Right? And then when both are variable, it would be D bar times LT bar, notice they're both average, times ZSL, all right? And then that would be the square root. And the reason why I need that is because it's going to be LT times sigma D squared plus D squared sigma LT squared. That's a little more complicated, but that's what it is. Essentially, again, this is really just the standard deviation of the demand during the lead time. That changes. That changes depending on the combination of the variability that you have. All right. But the basic thing is the demand during the lead time plus your safety stock. And remember, your Z value is the Z that is associated with the service level that you want. And in case you have forgotten a bit of that stuff, Remember, when you have a normal distribution, if, for example, we wanted a 95% service level, if SL is equal to 0.95, then this area in the tail will be 0.05. So our Z would actually be 1.645. If you don't remember how to do that, you have to go back to your normal tables and figure this out. But this is stuff that you've done before and are supposed to remember. All right, good. Okay, so here's an example. With we're looking at 50 units is mean demand during the lead time. Stock out cost is $40. Orders per year is equal to 6 orders per year. Carrying cost is equal to $5 per frame per year. So this is just an example where we have what we call a discrete probability distribution, and we're trying to determine um, the risk or the balance between stocking out or having, just looking at your stock out costs and to determine, and then your carrying costs to determine if you should, what you should actually keep as a safety stock. All right. So the reorder point right now is 50. That's if everything was just without any variability right now. So the 50 would allow you to satisfy if the demand is 40, 50, or 30. It will allow you to satisfy those. All right? Not a problem. So if we actually have, say, 10 units of safety stock, in other words, make our reorder point 60, then what would happen is that we would satisfy all the demands below 60, but there are 10 units that we could end up being short because the demand could potentially be 70. If we end up, making our reorder point 70, then we will actually have no stock out costs because we'll be able to meet all the demand, but we'll be carrying 20 units of safety stock, right? So, and then of course, if we kept it at 50, then we are not adding any more safety stock. In which case, we could actually run out we could actually be 10 units short 20% of the time, or 20 units short 10% of the time. So this is just an example to show you how you could consider how much safety stock that we should have. So with the 50, we are saying that we will just set our reorder point to the demand during the lead time, right? No safety stock. That's essentially what it is. And then, or we could have 10 units of safety stock or 20 units of safety stock. So let's take a look at our calculations here. If we decide that we're going to make the reorder point 70, which 20 units of safety stock, then it means that you have to hold 20 units all the time. And so there's 100, 20 by 5. That's your additional cost. There's no stock out cost because the 70 will cover all your demand. So your total cost is 100. What if you only decide to carry 10 units of safety stock? Well, you will incur $50 in terms of your holding costs. Remember, it's 10 times 5, 5 per frame carrying cost. And then you could run out of 10 units of stock because if you carry 10 units of safety stock, it means you have 60 units on hand. If the demand is 70, then you end up having to incur 10 units of stock out costs, right? But there's a probability associated with that. So the probability is 10% that the demand could end up being 60, in which case then you would be short by 10 units. So 10% times 10 is basically calculating an expected value. The probability of being 10 units short, right, in this case is 10% times the 10 units, right, multiply by the 40. And we're multiplying by 6. Why are we multiplying by 6? It's because there are 6 orders per year. So this could be, there are 6 times that this could possibly happen. And so we're multiplying it by 6 to give us a total cost of 240. When we add the 240 to the 250, our cost, if we carry 10 units of safety stock, is $290. And then if we don't carry any safety stock, we could actually end up being short, as we see here. Let me just 10 units, 20% of the time. That's when the demand is actually. Let's just go back to the diagram. So if the demand is 60, then we'll be 10 units short 20% of the time. If the demand is 70, we'll be 20 units short 10% of the time. So you see 10 units short 20% of the time multiplied by 40, which is the unit stock out cost. And then we're repeating this 6 times a year. Same thing here. Could end up being 20 units short if the demand is 70. There's a 10% chance the demand could be 70. $40 stock out cost, and then 6 times for the year gives us a total cost of $960. So it's very expensive not to have safety stock. So in this case, it makes sense to carry 20 units of safety stock, right? Because all you'll be doing is just carrying that, but you don't incur any stockouts. The reality is that the cost of the stockout is so high that it doesn't, compared to the cost of carrying inventory, it doesn't make sense to risk it. Okay, and so that's one of the example right here, just to show you that. So probabilistic demand. This is the case where we're showing that during the lead time, demand could be varying, or the lead time could be varying. I've already shown you all the formulas in the table that I have here. Sorry, right here. So you have all these formulas. So in fact, this should have just preceded this section right here. Okay. So this is just a diagram showing you that your demand could vary during the lead time, and so you could end up running out of stock, or you could end up having a lot of inventory left over when the items come. So you're seeing 3 different slopes that represents if there's a significant change from your demand rate, and you consume faster, then you could run out of stock. If you just continue, then no problem. And then here, if it's slower, then you're going to have stock left when the item actually arrives, right? So the formula, as we said, is really, the other point is your demand during the lead time times your Z value based on your safety, not your safety, your service level, and then your standard deviation during the lead time. The standard deviation during the lead time, really, you can compute it from that table that I showed you here. All right, these are the different variations depending on if the demand is constant, lead time is constant, demand is variable, lead time is constant, demand is constant, lead time is variable if both of them are variable. All right, so again, this diagram is just showing you exactly what I showed you before. No stockouts is our service level. Okay, this is the risk of a stockout. This is our reorder point. This is our safety stock. And so the safety stock essentially is this little piece that we're adding on, which is Z times our standard deviation of the demand during the lead time. And when you add the safety stock to the average demand, that's when you get the reorder point, and so on. So we have to compute, depending on the problem situation, what the demand, not the demand, sorry, what the standard deviation of the demand during the lead time is. And it depends on the combination that I showed you earlier. Okay. Example with no lead time. Okay. Let's see what this one is saying. You have average demand is 350 kits. The standard deviation of the demand during the lead time is 10 kits. Stock out policy is 5%. So the service level you want is 95%, which basically means that your Z value is going to be 1.645. I know that from when we did all the confidence intervals and all that good stuff. All right, but you remember you could get it from your normal table based on the area in the tail. Area in the right tail will be 5%. So you find what that Z value is because we assume the demand during the lead time is a normal distribution. So therefore your safety stock would simply be your Z value times your standard deviation during the lead time. Reorder point is the expected demand plus safety stock. And so it would be the 350 plus the 16.5 and so on. So in this example, you were just given sigma DLT. You were not told whether whether or not the lead time was constant, the demand was a variable, the lead time was variable, the demand was constant, or the lead time was variable and the demand was variable. We were not given all of that information, which is given the standard deviation of the demand in the lead time. However, it came about. So that's the easy case for you. If you were given the situation or the scenario of where not one is variable and the other one is constant, then you'd have to use one of those formulas that I showed you earlier. Okay. Now we're going to. This is just another example of the same thing that we're talking about, the safety stock, and where in this case the standard deviation of the demand, which means the demand is variable, but the lead time is not variable, it's constant. So they're just giving us this scenario. So this is a case where demand is variable and lead time is constant. And this is an example with that situation. You certainly can just review it. Main thing is that you're trying to calculate the safety stock. So for that scenario, remember I showed you that the safety stock would be Z times the square root of LT when the lead time is constant times the standard deviation of the demand. So that's exactly what you're seeing here. Constant demand, variable lead time. So in this case, to just be here. So your safety stock is Z times the demand, because remember the demand is constant, times the standard deviation of your lead time. That's the scenario that I mentioned as well. And then here's an example. The average lead time is the standard deviation of lead time is 1. And I believe there's an error in this problem. There should be 1, not 2. Service level 98%, which leaves you 2%, which means that your Z value is 2.54. So 10 by 6 days is the lead time. 10 units per day gives us 60. And then we have a Z value of 2.054. D, right, is our demand. And then the lead time, the standard deviation of the lead time is 1, but they had a 2 here, it should have been 1. In which case you get a reorder point of 80.54. So approximately 81 tablets is what we're going to keep. Sorry, in inventory while we're placing the order, which means our safety stock is approximately 20.54. Our reorder point is 81 tablets. And then if both of them are variable, this is the model that I showed you earlier, which would be, that's your standard deviation of demand during the lead time. So it looks like this. LT bar sigma D squared plus D squared sigma D bar squared, sorry, sigma LT squared. That would give you a standard deviation of the demand during the lead time. All right. Once you multiply that by Z or Z, then you will get your safety stock, and you could compute your reorder point. So that's what this example is doing. So you notice that the demand is variable, the standard deviation of the lead time. We should also have standard deviation of the sorry, standard deviation of lead time, standard deviation of the demand, right? Demand, lead time. Service level 95%, 1.645. And then we simply compute our standard deviation of the demand during the lead time, which we already saw the formula earlier. And once we compute that, we have our safety stock is 253. Our demand during the lead time, average demand during the lead time is 750. And so therefore our reorder point is 1,003 packs for this example. Okay, I'm going to stop here because this is quite long at this point and do a very short presentation on what we call a single period model and the periodic review model. Okay.